The sight of the moon eclipsing the sun has fascinated generations of onlookers. Our ancestors came up with a variety of explanations, some more accurate than others. But over the centuries, it turned out there was a lot more to learn from solar eclipses than just how they worked. The spectacle of a total solar eclipse has led scientists to new discoveries about the sun, the solar system, and the physics of the universe itself. When humans first started studying the heavens, we didn't know much about what our solar system really looked like. But solar eclipses did give us some hints. For example, that the sun must be further away from us than the moon. Ancient Greek astronomer Aristarchus wanted to know how much further, and decided to figure it out with simple geometry. Aristarchus deduced that when the moon is exactly half lit, the positions of the sun, moon and earth must form a right-angle triangle. So he measured the angle between the sun and the half moon, and used that to calculate the relative distances to the two objects. Since the angle is large, the sun must be many times further away from us than the moon is. And since they appear to be the same size in the sky, as we can see during an eclipse, the sun must also be many times bigger than the moon. Aristarchus was even one of the first to suggest that the Earth orbits the sun and not the other way around, though no one took that idea very seriously. Fast forward about 2,000 years, and Victorian scientists were taking solar eclipses very seriously indeed. Many intellectuals of that time were avid eclipse chasers, hoping to learn more about the sun and the strange halo of light visible around it during an eclipse. The founding editor of Nature wrote about the strange halo, named the corona, in the first edition of the journal, speculating on what it might be. Further study of eclipses proved that the corona was part of the sun, and not coming from the moon, as some had suggested. We now know that the corona is made from extremely hot plasma, shaped by the sun's magnetic field. It's only visible to the naked eye when the moon blocks out the much brighter light from the sun itself. Around the same time as they were studying the corona, scientists spotted an unknown line in the spectrum of sunlight during an eclipse. This line turned out to be a new element, helium, now known to be the second most common element in both the sun and in the universe itself. By 1919, a lot more was known about the sun. So in May of that year, Arthur Eddington used a total eclipse to study something completely different: how gravity bends light. He photographed a cluster of stars, visible near the edge of the eclipsed sun. But the stars looked like they were in a different position than usual. This was because the light from the distant stars had to pass so close to our sun that the sun's mass actually bent the light, an effect called gravitational lensing. It was the first experimental proof of Albert Einstein's general theory of relativity, and it made Einstein an overnight celebrity. In the almost 100 years since, people have continued to study the sun, the solar system, and the theory of general relativity. Today, most of this research no longer requires waiting for a total solar eclipse. Scientific instruments on Earth and in space can study the universe in amazing detail. But some scientists still travel to the site of total eclipses, and even chase the sun's shadow in super-fast jets, just to see what further secrets these spectacular events might reveal.